Hey, I'm Charlie Thompson, and welcome to the Chapter 7 lecture on climate change. Our chapter opener features this lovely photo of a melt pond on the Greenland ice sheet. The photographer referred to this as the Grand Canyon of Greenland, highlighting just how much melting is going on in Greenland. Before we get into the lecture notes part, there are a couple things I wanted to share with you. One of them is just a quick look at where we are. And where we are is hot. The 3 hottest years ever recorded were the last 3 years, and the warmest 11 years ever recorded on Earth were each of the last 11 years. So we are 11 for 11 with regards to warmest temperatures. It is not a fluke, it is a trend towards long-term high temperatures. You can see the dark red places here are warmest, recording their warmest temperatures relative to the reference period 1991 through 2020. And if we look at other examples, the 2023 record highs, 2024 record highs, 2025 record highs. This is a map made by a group called the Conspiracy of Cartographers, in which they take gas station maps, in this case a 1956 Shell oil gas station map, and on top of it they put the ocean to show us what it's going to look like when the glaciers stop melting. So this is a 1956 gas station map with about 66 meters of sea level rise. After Greenland and Antarctica, after those ice sheets have melted, sea level will rise and the Central Valley will once again be an enormous inland sea. Some of the high points, literally, the Sutter Buttes are going to stick out after that. They will be dry land, but as you can see, Sacramento, Davis, most of the Central Valley will be inundated, along with Berkeley and Oakland, much of San Francisco, San Jose, much of the Bay Area. Although we're not doing as badly as Florida, I think it's funny that one of the last places you'll be able to visit before Florida is submerged is Disney World, because Orlando is slightly higher. In fact, that's one of the reasons that Walt Disney chose Orlando for the location of Disney World. So looking at temperature averages, going back to 1880, you can see temperature averages were below average in the 80s. The blue colors indicate lower than average, the yellows. So right now in the 30s and 40s, we're getting balanced blue and yellow, and now the yellow is becoming more dominant. We're seeing more oranges, and the oranges will give way to reds as we approach the present. 2000s, we're looking at a lot of reds, 2010, 2013, 2017. And as we approach the present, you can see the global trend is much higher temperatures, especially at higher latitudes. Just like the temperature ranges are higher at higher latitudes, so is the temperature increase higher at higher latitudes. The tropics are warming more slowly. The higher latitudes, the Arctic, the poles are warming many times faster than the planet is on average. I love this quote. Climate change will manifest as a series of disasters viewed through phones with footage that gets closer and closer to where you live until you're the one filming it. Some examples of this would be the Greenland ice sheet. Again, we're back to Greenland. This is several inches of meltwater on top of the ice sheet. Absolutely surreal image of these dogs. They're not in the middle of the ocean. They are running on top of the ice sheet. Australia having record wildfires again. Australia followed the wildfires with record flooding. That's one of the things that we are seeing more and more of, is these extremes going from one extreme to another, going from either drought into flood, or in this case, fire into flood. We're seeing that all over the world. Sacramento, 2022 was the driest spring ever recorded, going back to the mid-1800s. Every January to March had seen more than an inch, sometimes 2 inches, like even back in 1972, in the middle of a drought, 2.39 inches. In 2022, Sacramento received 0.05 of an inch of rain in a period that they should have gotten an inch. That was in 2022, so they're back to record dry conditions. In 2021, they went from the longest dry season spell on record to the wettest October on record. And then they followed that up with the driest spring on record. So it went from dry spell to wettest to dry spell. NOAA publishes weather and climate events annually. They publish a monthly version of this as well, but nothing has really changed over the last several decades. That North America in 2025, the fourth warmest year on record globally. It was the third warmest. Europe, the second warmest. Asia, the third warmest. And these results are consistent with the rest of NOAA's annual publications, that year after year, hotter and hotter and hotter, and bigger storms and bigger floods and bigger droughts. Looking at 3-decade averages across the United States, you can see going back to the 40s, from the 40s to the 50s were warmer, the 60s were warmer, the 70s were warmer, the 80s were warmer, and the 90s were warmer. This isn't just the United States, it's a global phenomenon. Looking globally, if we go back to the 1950s, especially warmer, 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 warmest. And that trend is continuing. Again, just a reminder, 3 warmest years, 11 warmest years. And when we're talking about temperature changes, we're talking about 4.5 degrees difference. 20,000 years ago, temperatures were about 4.5 degrees cooler Celsius. That's about 8 or 9 degrees Fahrenheit. And the difference of 4.5 degrees is a half mile of ice over some places of the United States. So a small change in temperature has massive, massive effects globally. So from 20,000 years ago to the present, we've warmed by about 4.5 degrees over 20,000 years. And we're going to be seeing that amount of warming in the next less than 100 years. So among the things that are notable, the rate of change and the amount of change. So if we look and see what that means, 4.5 degrees cooler gives us over 6,000 feet of ice over Toronto. It gives us 2,000 feet of ice over Chicago, 3,600 feet ice over Boston, and 10,000 feet, 2 miles of ice over Montreal. So the difference of 4.5 degrees cooler to the present is 4.5 degrees warmer means that we've lost 2 miles of ice over Montreal, and we're going to be increasing the temperature by the same amount, by another 4.5 degrees or so. The global trend has been one of cooling over the last 1,000 years, right up to the Industrial Revolution, when the temperatures increased due to humans burning fossil fuels. And this incredibly confusing graphic is showing us that we don't know what the future will look like because we don't know what humans will do. Scientists are well aware if we increase CO2 to this level, this is what the temperature will look like, but because they don't know humans are going to act, we don't know how much CO2 we're going to add. Like if we decide to aggressively pursue renewables, we could limit warming to 1.5 or 2 degrees Celsius. If not, we're looking at 4, 5, 6 degrees of warming. And so at the present, the future is discretionary. There's choices that we can make now that will affect the future in a positive way. All right, let's look at the big questions. How do we know about past climates? The answer is proxy data. We'll talk about that. Why has climate changed in the past? We'll talk about that. The answer is Milankovitch cycles. How do we know climate is changing now? Because we can measure it, we can observe it. How do scientists model climate change? The answer is with computers. How are governments and people responding to climate change? Too slowly is the answer. So again, just to put things in perspective, looking at the last 800,000 years, although we've extended this back, we've found ice cores going back to 1 million years. So we're looking forward to extending this. But over the last 800,000 million years, carbon dioxide has gone from 300 to 180 to 280 to 180 to 280 to 180 to 280 to 180 to 280 to 180. So 300 parts per million is about the highest level of carbon dioxide we've seen over the last million years. We are now at 424 parts per million, so an incredible increase in carbon dioxide. almost a 1/3 increase in carbon dioxide just in the recent past, just going back to the 1800s. So we now are seeing higher temperatures, but also higher CO2 levels than any time in human history. Again, last 1,000 years, gradual cooling trend, right up until the Industrial Revolution when temperatures take off again. Looking at a longer temperature reconstruction, going back 6,000 years, the temperature has been cooling right up to the Industrial Revolution. Right now, we are about 1.5 degrees warmer than pre-industrial temperatures, on our way to 2, 3, 4, 5 degrees. We don't know. So how do we know about the past? And the answer is proxy records. Proxy records are not direct measurements. Direct measurements would be temperature records or other physical records, but proxy records are records of something else that you can infer from. So they tell us about past climate, things like fossil pollen, glacial ice cores, ocean bottom sediments, growth rings in trees. All of those can tell us what the temperature was like. They're not direct records like a thermometer would be, but if we know what, for example, the pollen was, we know what the plants were. If we know what the plants were, we know what the plant communities were, and we know what the temperature was. If it was oak trees, it was warmer. If it was pine trees, it was cooler. This lady is showing us a sediment core retrieved from the bottom of the ocean. They're brought up in big tubes and then cut in half so they can examine them under a microscope. These are 4 examples. We've got ocean sediment. We've got an ice core tube. Here is Dorte Dahl Jensen showing us an ice core tube showing bands of dust and debris in the ice. We can also see like exactly when the Romans started smelting different metals. We can see the Bronze Age. We can see the use of copper, iron. All those things are recorded in these ice cores. Also, fossil pollen. Fossil pollen is super useful because different species of plants have pollen that looks very different. And so if you know what the species pollen looks like, you can identify it under a microscope and say, these spiky balls are whatever, and this orange ball is whatever, and there's more spiky balls, so that tells us the temperature was whatever. So it's especially helpful if they're materials deposited year after year, like growth rings on trees or layers of sediment in lakes or the ocean, for example. Those are usually core samples, again, tubes, sediment from the ocean and lakes, taken using a machine like this. This is the Glomar Explorer. That was a drilling rig that went around the world and got ocean sediment samples. Here we've got a snow pit showing the layers of ice and snow as they're deposited. We can take cores of the ice, take cores of the snow, and then analyze it and discover what the temperature was like, what the atmosphere was like. Yeah, the idea that we can analyze million-year-old gas bubbles to find out what the composition of the atmosphere was like, I think that's totally cool. In the notes, if you look at the notes online, I've put a whole bunch of videos in. Here's one looking at how we study ancient ice. I put another one with Willie Dansgaard. You have to take a quiz about Willie Dansgaard. I absolutely love the Willie Dansgaard story because it's a cool example of how science can work. He had this idea about the relationship of oxygen isotope ratios and temperature. He set up a very simple experiment using beer bottles, and he confirmed his hypothesis. Tree ring cores, another sample of annual data that we can get is tree ring cores. And then by looking at an individual tree, we can tell what the climate was like for each year of the tree's life. That good years are wider rings and harsher years are narrower rings. So for example, these rings are really narrow. That was a tough year for the tree. These rings are really wide. That was a good year for the tree. And then by comparing different trees, we can create a record that extends back, and they've done this in Europe and the American Southwest. Both cases, they have compiled these records using different trees going back over 10,000 years in each case. So in America, we can use that to date pueblos, for example. I just read a book on tree ring dating and some of the other uses. There are people who specialize in tree ring dating of wood objects from the Roman era. And so they could tell us what kind of tree it was and when it was harvested and what the conditions were like. And then they can use that to figure out changing economic conditions within the Roman Empire from tree rings. Yeah, this is just showing that by using multiple trees, we can get a much longer record of tree rings. I've included a couple videos on tree ring dating. Another, I think the most interesting, the most amusing is pack rat middens. So this is a pack rat nest. Pack rats are rats that live in the American Southwest in these arid areas, and one of their habits is that they pee on the nests. And not only do they pee on the nests, but they will inhabit these for generations, so hundreds to thousands of years. So here we've got fossilized pack rat pee in the Grand Canyon, more pack rat pee. This lady is holding a chunk. She probably should be wearing gloves, but then scientists can take a chunk of this and wash out the pollen and date the whole blob to figure out how old it is. And by looking at the species in the pollen, we can know what the climate was like. And in the Grand Canyon, they've pushed this back, like I said, over 10,000 years. Absolutely fascinating stuff. Looking at a general overview of Earth's past. Starting 70 million years ago, there was a rapid warming that resulted then in a cooling trend. The warming is super important to us. We'll look at that in just a second. But the general cooling trend starting about 50 million years ago. And the idea is that the uplift of the Himalayas exposed limestone to weathering. And as rainwater hit the limestone, it absorbed so much carbon dioxide out of the atmosphere that it actually cooled the global planet. So kind of an interesting idea that plate tectonics would play a role in global climate change. So that spike was 56 million years ago. There was this sudden increase in atmospheric carbon dioxide levels. Took place over 20,000 years. So the change of 20,000 years compared to the present change over about 100 years. So incredibly fast. 200 times faster, the change that we're experiencing today. CO2 levels rose 600 to 800 parts per million. The temps were 5 to 8 degrees warmer. Sea level was 22 meters higher. So scientists are looking at this and saying, well, things got really bad. The temperatures rose globally. It resulted in upheaval and mass extinction events with biotic communities. And what we're experiencing today is even faster. And so the effects could be even worse from the present warming than the warming 56 million years ago. This is what it looked like in California 56 million years ago. Again, we are back to the Central Valley was mostly an inland sea and a couple high spots, but largely an inland sea. Over the last 5 million years, conditions have been slightly cooler than present. The current high temperatures are unprecedented in human civilization. The biggest change was over the last 100,000 years that the height of the last glacial maximum was 20,000 to 11,000 years ago, depending on what region you're looking at. So really the cold temperatures bottomed out 20,000 years ago, and then we've experienced warming, which melted a lot of the glaciers, but then we shifted into a cooling trend beginning around 6,000 years ago that ended with the Industrial Revolution. So for the last 2.5 million years, we've been in an ice age, and these 100,000 year cycles of 90,000 years of cold, and then 10,000 years of warm, and then 90,000 years of cold and 10,000 years of warm. Over the last 5 million years, we've had these fluctuating temperatures. Let's take a look at the whole trend. So going back 500 million years, we've experienced snowball Earth conditions. Temperatures were so cold that Earth was almost entirely covered with snow and ice. And when you're looking at this diagram, it's important to look at the time scale. So here we're looking at divisions of 100 million years, 10 million years, 1 million years, 100,000 years, and then thousands, 5,000 years. So this is, from here to here, we're looking at 4 million years. And from here to here, we're looking at 50 million. And from here to here, we're looking at 3 million. So as we get closer to the present, it's like we're zooming in on the time scale. So the time scales are not all the same. Like this spiky, this is the glacial and interglacial cycles. 10,000 years of warm, and then back into 90 of cold, 10,000 of warm. So that's been happening for the last 2.5 million years. So these spikes are really these spikes. And then we had a warming trend bringing us out of the glacial period, followed by a general cooling trend, followed by an abrupt warming trend. Snowball Earth, scientists are still discovering more and more about Snowball Earth, but we think what happened was Earth started to cool, and so there was more snow and ice. That led to cooling temperatures, more snow and ice, cooling temperatures, more snow and ice, cooling temperatures, until Earth pretty much froze over, almost entirely covered with snow and ice. I've put a link to a PBS video explaining how that happened down there. But once Earth was covered with snow and ice, there was nothing that was going to bring us out of that, except that volcanoes kept erupting. As we'll see later, volcanoes have a cooling effect on Earth, except in this case, the CO2 emitted by the volcanoes wasn't absorbed by plants because they were all covered with ice. And so CO2 levels rose until the feedback loop switched from colder, more ice to now warmer, less ice, warmer, less ice. And then that feedback loop of as the planet warmed, it melted the ice, which warmed the planet, which melted the ice. That brought us out. But we think, scientists are pretty certain that at least twice Earth was completely covered with ice and snow. So we've got Snowball Earth, we've got the PETM, that thermal maximum period, that brief spike. Again, the current warming is 200 times faster than this. And then we have the uplift of the Himalayas, the uplift of the Himalayas causing perhaps this global cooling trend. Cooling trend continued. Here we see the beginning of the Pleistocene 2.5 million years ago. Oh, we also saw in here 65 million years ago, the extinction event that killed off the dinosaurs. Then we've got over the last 2.5 million years in the Pleistocene, we've been in this cycle of 90,000 of cold and 10,000 years of warm, followed by a warming trend that melted the big ice sheets, followed by a gradual cooling trend and a warming trend. So here we've got the last 800,000 years. We've got warm, cold, warm, cold, warm, cold, and now we're spiking, going back into a warm situation. Although that warm situation is warmer than any time in the last several million years. Looking at the last 20,000 years, well, longer than that is the Pleistocene. The Pleistocene began 2.5 million years ago. The last glacial maximum lasted from 110,000 years ago to 10 or 20,000 years ago. We have been warming since then. Again, here's that cooling trend going into the warming trend. Some other things happened. There was a brief warm spell that allowed the Vikings to settle out across Greenland, first Iceland and then Greenland, and then the temperatures returned to colder conditions and the Vikings abandoned the settlements in Greenland. There was a cold period, AD 1250 through 1850, likely through volcanic activity. So volcanoes emit CO2, but they also kick a lot of ash into the atmosphere that blocks the light and heat. So we think it's related to volcanic activity from 1250 to 1850, but the little ice age from 1250 to 1850, that cooler period, likely because of volcanic activity. But the reason for this cycle of 90,000 years of cold conditions and 10,000 years of warm conditions, the Milankovitch cycles. And those are three orbital variables. Earth's orbit changes shape on a cycle of 100,000 years. The direction that Earth's axis is pointing changes on a cycle of 26,000 years, and Earth's axial tilt changes from 21.5 degrees to 24.5 degrees on a cycle of 41,000 years. The Serbian mathematician Milutin Milankovic put all these together, figured it out during World War II, doing math by hand. And so these three orbital variables are the change in shape of Earth's orbit from more elliptical to more circular, the direction that Earth's axis is pointing in, like right now if the sun was over here, this would be northern hemisphere summer. We are farthest away in northern hemisphere summer, and we are closest in northern hemisphere winter. But in 13,000 years, it'll be the opposite. We'll be closest when the northern hemisphere is pointing towards the sun. We'll be farthest when the northern hemisphere is pointing away from the sun. And then the tilt changes from 21.5 to 24.5. 24.5, there's more seasonality. 21.5, there's less seasonality. Milankovic put these three variables together and realized that they correspond very, very well with the stages of glaciation. So we've got changes in the shape of orbit, shape of Earth's orbit going from more circular to more elliptical on a cycle of 100,000 years. We've got axial precession. So right now, the northern hemisphere is pointing towards the sun when we are farthest away, so our summers are a little cooler. In 13,000 years, when it's northern hemisphere winter, we'll be farther away from the sun because we will be pointing away from the sun when we are closest, and we'll be pointing at the sun when we are... Wait, did I get that backwards? Right now, we're farthest in the summer and closest in the winter. In 13,000 years, we will be closest in the summertime and farthest in the wintertime, so we will have more extreme seasons. And then last but least, the changes in the tilt on a cycle of 41,000 years just create more and less seasonality. So about that, going back to the beginning of the Pleistocene 2.5 million years ago, one of the things scientists have uncovered recently is a shift from the 41,000 year tilt cycle being dominant in creating these conditions of glacial and interglacial. And then around 1 million years ago, it shifted to the shape of Earth's orbit being the main driver with a 100,000 year cycle. So interesting science still being done with understanding the Milankovic cycles. So the Milankovic cycles are the reason for glacial and interglacial periods. Let's look at some other factors that may or may not be influencing Earth's climate change. One of them, sunspots. More sunspots, more activity from the sun, warmer conditions, fewer sunspots, colder conditions generally on Earth. The period from 1645 to 1715 is called the Maunder Minimum. It was associated with fewer sunspots. Let's take a look at a graph. So the sun puts out more and less energy on an 11-year cycle and also on a 22-year cycle of more and less energy. During the Maunder Minimum, temperatures were slightly lower, but not enough for solar activity to be the driver of climate change. Like you can see, there was less activity, and now we're in a period of slightly decreasing. Before 1950, solar activity has been decreasing, and you can see the temperature has increased during a time of decreasing solar output. So it's not changes in Earth's, the amount of energy that Earth is receiving from the sun. That is not the driver of climate change. Interesting thing is when there was more ice at the depths of these glacial periods, there was so much ice that sea levels globally were so low that you could walk from Australia to Papua New Guinea. You could walk from Indonesia to Thailand. You could walk from France to England. On the East Coast, the shoreline was 60 miles offshore where it is today, and there was no San Francisco Bay. Sea level was so low 10,000 years ago, 16,000 years ago, that all of this was dry land 10,000 years ago. People were living in this area called Doggerland, and fishing boats today bring up things like combs and other household implements off the bottom of the North Sea because people were living there 16,000 years ago to 10,000 years ago. One of the interesting aspects of plate tectonics and climate change is when all the continents were together, there would have been way more continentality, so the deserts would have been desertier, and those polar climates would have been shifting from super hot, like the Siberian equivalent of warm summers, and below freezing winters would have been even hotter and even colder. So more continentality when the continent was bigger. Another interesting thing, the Panama Land Bridge, when it was opened 20 million years ago, the equatorial current would have gone all around the world. But then after the Panama Land Bridge formed, the Gulf Stream got diverted. So you can't have the Gulf Stream without the Panama Land Bridge diverting the warm current back towards Europe. Volcanic eruptions tend to cool temperatures. The volcanic eruptions emit carbon dioxide, but for the most part, they result in colder temperatures for a couple of years. If we look at Santa Maria and Agang, El Chichon, Pinatubo, all of those dropped global temperatures for a couple of years. Yeah, I just included this because the eruption of the Long Valley caldera covered parts of California in 600 feet of glowing ash, and the ash fall from the Long Valley caldera when it erupted 760,000 years ago can be seen across the U.S., like way farther east than I would have expected. Okay, let's talk about feedback loops. So feedback loops are when the behavior of the system affects the output and the output affects the behavior. The output affects the behavior. The output affects the behavior. So a couple of feedback loops to look at: ice albedo, water vapor feedback loop, and the ice elevation feedback loop. All of these are positive feedback loops. The ice albedo feedback loop is a positive feedback loop. When the ice melts, it exposes dark materials that absorb heat that melt the ice, that exposes dark materials that melts the ice. And that process continues and continues and continues. Also, as Earth warms, there are more wildfires, and the wildfires deposit ash on the ice, darkening the ice, increasing the melt rate. Yeah. Dark ash falls on the white ice, and then you get more and more and more melting. So here we've got a picture showing the dark water compared with the bright ice reflecting heat. So the snow and ice melts. Dark surfaces are revealed, which increases the temperature, which melts the ice. So dark surfaces are revealed, which increases the temperature, which melts the ice. This process continues. Here we can see what the dark ice looks like on the edge of Greenland. This is one of Jason Box's photos. Again, the Greenland ice sheet at the edges. As the ice melts, this dark material gets more and more concentrated at the surface, melting the ice more quickly. Close-up showing just how dark the ice is. An even more close-up shot showing how the black carbon and the algae become concentrated and create darker ice that then melts it faster. So feedbacks are related to tipping points. The kayak, if you're sitting in a kayak, that's a really good example. If you're sitting in a kayak, you can lean over a bit. And if you straighten up, the kayak will come back to horizontal. If you lean over a little bit more, the kayak will still come back. But eventually, if you lean over too far, the kayak will flip over. And so it goes from one steady state upright to another steady state flipped over. And once you hit that tipping point, it will keep moving. Once that threshold is crossed, we will expect for the process to continue. And so even if you reduce greenhouse gases, even if you try to stop leaning as much, it's too late. You are tipping over. So tipping points and systems are connected. Let's look at some more examples. I've included some videos explaining how this works. A video on some places that will undergo radical transformation after these tipping points are hit. The water vapor feedback. Water vapor is the most abundant greenhouse gas, the most abundant natural greenhouse gas. Carbon dioxide and methane are super important, but water vapor is emitted naturally. So what happens is more evaporation leads to higher humidity. As the planet warms, there's more evaporation. The water vapor in the atmosphere absorbs heat, which warms the atmosphere, so there's more evaporation. Because there's more evaporation, there's more water vapor in the atmosphere, which warms the atmosphere, so there's more evaporation. Every 1 Celsius increase in atmospheric temperature increases water vapor by 7%. So right now, we're at about 1.5 degrees warmer, so there's about 10% more water vapor in the atmosphere today than a couple of years ago when it was cooler. So we see more flooding. We see higher impact precipitation events, that just a rainstorm is now delivering as much rain as a hurricane used to, for example, or a smaller tropical storm delivering as much rain as hurricanes used to. More water vapor in the atmosphere. Stefan Rahmstorf is going to talk in this video about the ice elevation feedback loop, that if I just use Rahmstorf's head as the top of the ice sheet, because Greenland has over 10,000 feet of ice, the elevation is over 10,000 feet, so it's cold. But as the ice melts, it is now at a lower elevation, and so the air around it is warmer, so it melts faster. And because it melts faster, now it's at a lower elevation, and the air is warmer, so it melts faster. And that process continues until the ice is gone. So once a tipping point is reached, once that you get what's called a runaway feedback loop. So as Stefan Rahmstorf will explain, it's entirely possible we have crossed the threshold for the tipping point for the complete loss of Greenland. It'll take thousands of years, but once it's already started melting and it's below that crucial threshold, it won't stop melting because conditions are just too warm. Thank you, Stefan. So the carbon budget is super important. Carbon budget includes carbon dioxide, which is one of the main drivers of changes of temperature. We will talk about sources, sinks, and flux. Sources is when carbon dioxide is emitted. Sinks is when it's absorbed, like by the oceans, by the atmosphere, by trees. And then flux is carbon dioxide moving between sources and sinks. So again, the carbon sinks, that's where carbon is stored. The atmosphere, fossil fuels in the ground, in plants. Flux is carbon moving back and forth between sinks. The amount of carbon in flux is just a tiny, tiny, tiny fraction of the total carbon. That's another important concept. Finally, the exchange of carbon between systems is the global carbon budget. It used to be balanced, but it's not because humans have thrown it out of balance. How have we done that? We have done that by burning fossil fuels, clearing forests, all of that producing carbon dioxide. The oceans have absorbed much of our carbon dioxide. Unfortunately, this is causing ocean acidification. When the ocean becomes more and more acidic, this is causing problems with microorganisms, things like oysters and clams, especially even commercially raised oysters. For example, the Hog Island Oyster Company up in Humboldt Bay is having to add chemicals to their water that they're raising the baby oysters in because the water is too acidic, that it actually is interfering with their ability to make shells from seawater. Ecosystems have taken advantage of more carbon dioxide by growing. The plants are growing more rapidly. We can't compare tree rings from before 1950 to tree rings after 1950 because there's so much carbon dioxide added to the atmosphere that plants are growing more quickly now. So here's the carbon budget. The white numbers, that's carbon in sinks in billions of tons or gigatons. So 10,000 gigatons stored in the ground, 6,000 gigatons stored in ocean sediments, 30 to 40,000 gigatons stored in ocean water. The ocean is absorbing most of the heat and most of the CO2, which is good for us, bad for the ocean. The numbers in yellow, that's the in flux moving from the atmosphere into plants, 120 gigatons, and then every year plants are emitting 120 gigatons, except humans are emitting 10 to 20 gigatons a year. Part of that is being taken up by photosynthesis, both on land and in the ocean, and part of it is being absorbed by the ocean, part of it is being absorbed by the atmosphere, but most of the leftover CO2 is being absorbed by the ocean, which is making it more acidic. But this was balanced. This was a balanced system until humans began emitting so much carbon dioxide that we've thrown it out of balance. How do we know? Because it's measured at Mauna Loa. This is the Keeling curve, named after Charles Keeling. He was a researcher at Scripps down in San Diego who decided to start measuring carbon dioxide on his honeymoon back in 1959. This is the longest running record of carbon dioxide on Earth that we have. The current administration has eliminated funding so that we can no longer measure carbon dioxide and compare current carbon dioxide to past carbon dioxide. How do we know the climate is changing? By every measure available. At the super basic level, higher temperatures everywhere, over the land, over the oceans, higher temperatures in the lower troposphere. The troposphere is getting warmer, and so less heat is passing through to the stratosphere. So the upper atmosphere is actually slightly cooler because the troposphere, because of CO2 in the troposphere holding on to that heat. Higher ocean temperatures, higher air temperatures, higher land temperatures, rising sea levels, decreasing sea ice, melting glacial ice, increasing water vapor in the atmosphere, increasing heat content in the ocean. By every objective standard, we are changing the climate dramatically. Yeah, that's just saying the same thing. Rising temperatures, melting ice, rising sea levels, increased water vapor. Here we've got temperatures looking at 1940 or something going to 2025. Here we can see 2024, the warmest year ever recorded. And it was also the first year that we recorded average temperatures across the globe greater than 1.5 degrees above the pre-industrial levels. So if we look at, again, anomalies, since 1976, every year after 1976, the temperature has been above average. So if you were born in 1977, you have never spent a year on Earth where the temperature was below or at average. Every year after 1976, the global temperature has been above average. Every decade from the 1960s on has been warmer than the decade before. That trend is not slowing down, and the 2020s will be the warmest decade ever recorded. It's just another graph showing the temperatures are continuing to increase. In fact, the increase is increasing. We're seeing less ice on the sea and in the land. Glaciers globally are melting and decreasing. Arctic sea ice, looking at the amount of sea ice in the 80s, less in the 90s, less in the 2000s, less in the 2010s, and 2026, we are seeing a record low amount of Arctic sea ice. Looking at Greenland and Antarctica, losing ice year after year after year after year after year. Greenland and Antarctica both losing massive amounts of ice. And the area and the elevation of the ice that is melting is increasing. So there's melting even at the top of the ice sheet in Greenland. There is melting of ice shelves. So this white ice is ice that's on the land. This, if it's got a color on this map, that is an ice shelf where the ice is thick but floating on the ocean. And these ice shelves are disintegrating and breaking up, and that allows the ice on the land to flow more quickly into the ocean, which raises sea level. So here we've got a floating ice shelf. Recently, they've sent some remotely operated vehicles down below the ice shelf, and they discovered there are these amazing new undiscovered warm currents that are melting these ice shelves from the bottom. One of the issues that scientists are looking at is, in some places, the surface, the ground, actually slopes downwards as you move inland. And so once this starts melting, the melting will increase it'll proceed at a faster rate. It'll melt faster and faster and faster, and then the grounded ice sheet will be floating, and then it'll break up. I included a couple of videos in the notes, if you look at the notes, or the YouTube playlist, how they measure glacial melt in Iceland, how they measure glacial melt in Greenland. There's Jason Box. How they're using drones to look at the changes in albedo to the ice sheet as the result of melting, and ash and algae growing in new places. So melting ice in the oceans, melting ice on the land, also melting ice in the soil. And we call that frozen ground permafrost. So permafrost is frozen ground in the Arctic and Antarctic and some places at high elevation, like in the Himalayas. So the ground is frozen year-round, and when it thaws out, if it thaws out in the spring, the dead stuff in the ground gets decomposed by microorganisms, and they break down the dead material and release methane. And when they release methane, methane is a very powerful greenhouse gas. It's 30 to 80 times more powerful than CO2 at absorbing heat. So it absorbs way more heat than CO2. And then once that methane's in the atmosphere, it warms the atmosphere, which melts more permafrost, which releases methane, which warms the atmosphere. One of the things that we're looking at are these drunken forests, that the frozen ground actually provided a foundation for trees. And then once the ice thaws to mud, the trees fall over and die, and then they're going to get decomposed, and that'll emit even more methane. I've included this video with Dr. Katie Anthony at the University of Fairbanks in Alaska. She's been studying methane released in these melt ponds across the Arctic. These ponds, they freeze over in the winter, but the ice then traps methane, and they're able to measure how much methane is being released in Arctic lakes as a result of warming temperatures. Permafrost is causing problems with buildings in the Arctic, that when the ice melts and becomes mud, often buildings are collapsing, forests are collapsing, lakes are draining, which is going to change the water cycle in the Arctic. All of this is really bad news for people in the Arctic as the permafrost melts. I mentioned the amount of carbon in permafrost, so we're looking at the amount of carbon in permafrost here, kilograms per square meter of carbon in the top 30 inches of the soil. Another study showed that as the permafrost melted, there was more photosynthesis. So plants absorbed 1 gigaton across the study area during the time that they were looking at it, but the melting permafrost and the breakdown of the dead material released 1.7 gigatons of methane. So the Arctic has become an emitter of greenhouse gases as it melts, which is another bad feedback loop. As the Arctic melts, the feedback loop results in more melting. Higher temperatures, more melting. Higher temperatures, more melting. Sea level, because of melting ice on the land, the glaciers on the land melt, the water runs into the ocean. Also, as the ocean warms, the water expands slightly. A quarter of sea level rise is just due to thermal expansion of the water. For the test, I think the best answer is we're looking at 6 feet of sea level rise. By 2100, I think we're looking at about, I think the agreement between the various studies indicates we're looking probably at 6 feet of sea level rise. Some of the other studies weren't looking at some of the feedback loops that we're aware of now. And so I think we're looking at 6 feet, 2 meters. Here we've got a Pacific Island nation. This is just flooding. This is going to happen twice a day. This is the main road on this island, and here's the ocean washing over that. More South Pacific flooding. I think this is Kiribati, Vanuatu, Tuvalu. Some of the island nations are trying to find a home. Tuvalu is going to have to, everybody in Tuvalu, the entire nation of Tuvalu is going to have to move to Australia because their country will be underwater. Once seawater starts washing over the land, you can't grow crops anymore. Whatever fresh water was there is now salt water, so you can't grow crops, you don't have fresh water, and so hundreds of thousands, if not millions of people are going to have to relocate just because of rising sea level. Here we can see, I think this is Kiribati after a tropical storm came through. This is the main drag on one of the cities. And you can see this is just, it's impossible to live like this. And the tragedy of people having to leave is something that I can't really relate to. These Pacific Island nations, people have been living there for thousands and thousands of years on these islands. And so their ancestors are buried there. They're going to have to abandon their ancestors to rising sea level beneath the waves. I just can't imagine what a tragedy that's going to be for them. Other changes that we can look at: increased water vapor. As the atmosphere warms, there's more evaporation, so there's more water vapor, which warms the atmosphere. Hurricane Patricia hit sustained winds of over 200 miles an hour, the strongest West Pacific or East Pacific hurricane recorded at the time. Sustained winds of 200 miles an hour because of record high temperatures in the ocean. Same thing with tornadoes. We're seeing stronger tornadoes as the result of more water vapor. This is looking at heavy precip. Heavy precipitation events are increasing. This is looking at energy exerted by hurricanes every year. That's also increasing as sea surface temperatures are increasing. We are seeing an increase in extreme events, heat waves, droughts, heavy rainfall events, flooding events. All those things are becoming more common. But unfortunately, after 6 years of extreme events, our brains just adapt, adjust, and go, oh, that's the norm. Yeah, we should be having floods every year. That's the way it's always been after 6 years, which makes it more difficult to say, no, this is new, and this is really bad, and we should change it. So, yeah, it's good that humans are that adaptable, but it's bad that we just sort of get used to it. I was looking for evidence of flooding for one specific example and was just blown away by how much evidence of flooding there was, just looking for a good image of flooding. Same thing, wildfires, catastrophic wildfires increasing as a result of climate change, warmer temperatures. Warmer temperatures. Why? Well, the glacial interglacial cycles are because of the Milankovitch cycles, but the present climate change, the anthropogenic or human-caused climate change, is because of greenhouse gases, mainly carbon dioxide. Methane is another one, nitrous oxide, and chlorofluorocarbons are other greenhouse gases, but really it's mainly carbon dioxide. Carbon dioxide, record levels, in the atmosphere. We've never had this much CO2 in the atmosphere. At the same time, there were humans on Earth. Fossil fuels and also cement making. Cement making uses a lot of fossil fuels because they have to cook the rock in order to make it into cement. So fossil fuels and cement. Methane from natural gas and petroleum systems, agriculture. Methane is even more powerful than carbon dioxide at warming the atmosphere. Nitrous oxide from synthetic fertilizers, also warming the planet. Nitrous oxide from synthetic fertilizers, it's just a bad system. I'll talk about that in a minute. Chlorofluorocarbons, at least, are decreasing. The world said, hey, these CFCs are really good as a refrigerant, but they're messing up the ozone layer, and they're also accelerating global warming. And so globally, we are phasing out the use of the more reactive greenhouse gas CFCs. We're replacing, for example, CFC-12 with other chlorofluorocarbons that do not absorb as much heat in the atmosphere. Oil use, burning of fossil fuels, is a major driver of the current climate change. The US, Canada, Australia, Norway, some of the leaders in use of oil, which is not good. It's time for a keyword: forcings. Forcings are things that either make the planet warmer or colder. Anthropogenic factors are created by humans. So positive forcing makes it warmer. Negative forcing makes it cooler. If we look at all of the different forcings, carbon dioxide is by far the biggest, most important forcing. Let's look at this. So natural forcing changes slightly more insulation, 0.05 watts per square meter, but it's greenhouse gases, 2.83 watts of warming from greenhouse gases. Air pollution has warmed the planet by almost a half a watt. This is the diagram out of your textbook. This is one of the IPCC's diagrams showing human-caused and natural changes, so slightly warmer due to changes from the sun, but here you can see CO2 and other greenhouse gases are the main driver. The bars on this side are positive, making it warmer. The bars on this side are negative, making it cooler. So aerosols, anthropogenic air pollution is making the planet slightly cooler, but if you add up everything, we are warming the planet by about 2.4 watts per square meter. So the current warming, the current imbalance. So every day all over the world, 2.4 watts per square meter come in and then stick around. They don't leave. So if we add it all up, global surface temperatures have increased by at least 0.8 degrees. A couple years ago, we hit 1.5. We are in a low output state from the sun, so we should have been slightly cooler. Volcanoes tend to cool temperatures for a couple of years. The dominant factor in the current climate change is human contributions. Looking at climate models, and I'll talk more about how models are created in just a minute, but if we look at what the models in black say should have happened and compare that to what really happened, the models are getting more accurate. So breaking it down, just looking at changes in insolation, you can see there's changes every year. Changes due to volcanic activity, so cooling after Mount Pinatubo, cooling after Agong and El Chichon. Changes in temperature due to El Nino. Changes in temperature due to greenhouse gases. So you put all those human and natural factors together and you get the red line of what should have happened. And now the climate models are very accurate and do a really good job at recreating what happened in the past. So they're all computer models based on weather forecasting models, looking at all the different factors going on with the climate system. The whole world is divided up into a big grid, like a latitude-longitude grid. Over time, the grid squares have gotten smaller and smaller and smaller. A couple decades ago, like the climate of the U.S. would have been represented by 2 grid squares. So everybody on the East Coast and everybody on the West Coast, you just get the one grid square. But now these little squares are small enough that they could say, oh, here's what it's going to be like in Sacramento as opposed to Elk Grove, as opposed to Dixon, for example. They look at layers going down through the ocean, layers going up through the atmosphere, and then they set the conditions they initialize it by setting the initial conditions for all the grid squares. So you can do that using known data. So for example, if you wanted to test your model, you could set the conditions to all over the world to the way everything was January 1st, 1960. And then you let the model run forward and you compare what the model says happened to what really happened. And then you can go back and tweak the model and say, well, we think that the effect of, for example, water vapor is actually more important than this model. So you make the water vapor more important. And then you run it again and you see what happened. And if you do this hundreds and hundreds and hundreds of thousands of times, you end up with very accurate models. I don't know why this picture is here. It's a supercomputer. I just found out that supercomputers from the 80s are roughly 100,000 times slower than the most current iPhone. So computers are getting better. The models are getting more accurate, but they still don't have any good news for us. Right. I mentioned this. You can change the initial conditions with these different scenarios, run it forward in time, and see what the output is. So, for example, looking at climate model solutions that did not include greenhouse gases, very different from what actually happened. Once you put the greenhouse gases in, you get good agreement between what the models say should have happened and what actually happened with regards to temperatures on Earth. So this is the answer to the question, well, if they can't really predict weather for next week, how do we know what the climate was like? Well, we know what it was like in the past, and we have a pretty good idea why it was like that. And so if we know what causes climate to change, we can put those elements into the model and run the model. So climate change modeling, it's not like you're trying to predict an actual degree on a day. You're trying to predict general trends across larger areas, which is easier to do. So this is what I'm talking about. These global climate models don't predict individual temperatures. They can tell us what the temperature change is going to be across an area. Often the numbers represent the change in energy in watts per square meter. So, for example, this model, SSB 2 to 4.5, represents 2 to 4.5 watts of warming. Remember, the current warming is 2.4 watts. So if we look at these different models of what the future might look like, they're based on assumptions of what society does. The RCP 8.5 showing 8.5 watts of warming was based on, they just projected current trends out. That's the business as usual, the worst case scenario. We've actually warmed slightly more quickly than that. We are at 1.5 watts of warming. The 2.6 is even higher than the current amount of warming of 2.4 watts. So the 2.6 represents an aggressive abandoning of fossil fuels and an aggressive embracing of renewables that tries to keep warming to, this says 1 degree. I think we're looking at closer to 1.5. But the most probable outcome based on current events is 8 degrees of warming by 2100. So you're looking at 6 feet of sea level rise, 8 Fahrenheit degrees of warming by 2100. And just to remind you, 4.5 degrees cooler gives us a mile of ice or 2 miles of ice over Montreal. We are going from 4.5 cooler to 8 warmer by 2100, probably. Unless we make radical changes right now. And that's what this would look like. So if we keep cranking out greenhouse gases, we're going to be living in a much warmer world. But if we start to embrace more renewables, which is the cheapest way of making electricity, we could have a much more habitable planet. And that's going to make a difference in your life. If we aggressively adopt renewables, we could keep warming to 1.2, 1.5 degrees. If we don't, we could be looking at 4, 5 degrees of warming by 2100. So again, the Arctic is warming faster than the tropics, but the difference between aggressive renewables and business as usual is pretty obvious, that we could have 20 Fahrenheit degree warmer conditions in the Arctic if we don't change our ways soon. Reminder, 4.5 degrees cooler, you get Earth with 30% of the land covered with ice. Florida was huge. The East Coast was way offshore. There was no Bay Area. It was all dry land. You could walk from Sacramento to the Farallon Islands, which are off the coast of San Francisco. All of this was dry land when there was that much ice on the land. 2 meters, even 2 meters, which is what we're looking at by 2100, you can see massive changes in the Bay Area, massive changes just south of Sacramento, with all of this potentially being wet land. If we lose Greenland, I can commute to work by kayak. If we lose Greenland, if we lose Antarctica, then we've got a massive inland sea again. So this is what the future can look like unless we make big changes right now. So here's sea level rise, 66 meters of sea level rise on the west coast. This is looking at just a couple feet of sea level rise. So by 2100, New Orleans could be underwater. Miami Beach, much of Florida underwater. The East Coast is going to have a bigger problem with sea level rise than the West Coast because the East Coast is much flatter. So because the slope is so shallow, a small difference, a small vertical difference makes a big horizontal difference in where the coastline is. Again, I think we're looking at 6 feet of sea level rise by 2100. I think that's the best, the most realistic number to use. This is New York City after Hurricane Sandy. This is the ocean washing over the sidewalk here. They have spent over $1 billion trying to stormproof the subways, for example. And I remember when I read that and I thought, oh, I had never even thought of the subway. But if you've got seawater running over the ground and you've got subways, you're going to have useless flooded subways. So New York is taking climate change seriously, or at least reasonably seriously. I've included a bunch of videos about Miami's real estate market and what's going on in Florida. More videos about Florida. And yeah, this is called nuisance flooding. And in Florida, because the governor has forbidden state workers to use the terms climate change or sea level rise, this is called clear sky flooding or nuisance flooding. But this is just the ocean. This is just high tide. And then that seawater gets into concrete and causes it to fall apart, which can cause a problem with collapsing buildings. They don't appear to really care. More sea level flooding in Key Largo. I put another video about Tangier Island, which is in the Chesapeake Bay off Virginia, and it is sinking. This is the ocean. This is one of the sidewalks. And the residents there since the 1800s have watched their island get washed away and washed away and washed away, but they are denying it's because of climate change, which I just don't get. Interesting video, interesting people. Same problem in Huntington Beach. Here we've got nuisance flooding in Huntington Beach. It's also happening across Southern California. Every year, the high tides, the king tides, get lots of news coverage. Marin was flooded this year. So it's not just an East Coast thing. Let's talk about possible futures. So the IPCC, the Intergovernmental Panel on Climate Change, they won a Nobel Prize for their outstanding scientific work saying the climate is changing. They are 99% certain that it will be hotter. They are 99% certain that sea level will continue to rise and that the ocean will continue to acidify. There'll be changes to runoff. If there's more evaporation, then you're going to have drier conditions, which will be an issue in the American Southwest. It'll be an issue for India and China, especially as mountain glaciers melt away, and then there will not be meltwater in the spring. The IPCC like I said, won a Nobel Prize for their scientific work on climate change. The scientific consensus is almost unanimous. There are some papers that reject global warming. There was a super famous study that looked at almost 14,000 papers, and they found 24 out of the 14,000 that rejected global warming. A more careful analysis of those 24 found errors in all of them. Each of those 24 papers was fundamentally flawed. They did cherry picking, which is when you just don't include data that doesn't support your idea. Another issue is that the contrarian papers did not agree with each other. All the climate change papers agree with each other. The ones saying climate change is caused by humans, mainly carbon dioxide, and it's going to be bad. Those papers agree on the causes and what the effects are going to be. Those 24 papers, each of them had their own wrong idea. They didn't even have a consistent single wrong idea. Each of them had their own wrong idea. Some of them were looking at, oh no, it's the sun. Oh, it's orbital cycles of other planets, or it's ocean cycles or something. So these papers contradict each other, but they're still all wrong. And every single one of those papers, when the experiments were performed correctly, they agreed with the scientific consensus. So there is no denial that the planet is warming because of humans. The only people that are selling you anything other than that are the fossil fuel companies. Yeah, I just think this is funny. Cold weather causes people to be more skeptical of climate change and global warming. But the good news is it's warmer. The global trend is warmer and warmer and warmer. What can you do? Well, you can get informed, which is super difficult because you're bucking a fossil fuel industry that's been spewing propaganda for decades. So probably most of the stuff that you've heard about global warming is wrong because it came from the fossil fuel industries who have a multi-billion-dollar reason to keep us confused. All kinds of things would help. Sustainable agriculture, shifting to organic methods rather than using synthetic fertilizer would do a great deal to slow global warming. Geoengineering is the idea. Oh, yeah, there's some nice organic agriculture. Geoengineering is a super terrifying concept that many people are saying, oh, humans have messed up the climate, so humans should fix the climate by messing it up hard in a new way, which is a very bad idea. I'm unaware of any big projects that humans have taken on that didn't have catastrophic, unexpected, unintended consequences. Like across Egypt in the 50s, the Soviet Union built these big dams to prove that they were a better political system. And what it did was shut off the flow of new soil every year when they flooded, and it created a huge breeding ground for these parasitic worms that burrow into your eyes and make you blind. So they increased river blindness, but they didn't actually make things better. They made things worse. And so these geoengineering ideas are ideas like fertilizing the ocean so algae will grow and then die and sink to the bottom, taking CO2 with it, or putting giant umbrellas in space, or putting chemicals in jet fuels so that as planes fly around, they make chemtrails that don't go away and make the atmosphere more reflective. So the concern is that we don't know what we're doing. And if we do that, it could do something like disrupt the Asian monsoon. And now you've messed up the rains that 3 billion people are depending on for their rice crop. And we could see catastrophic changes to the climate as the result of geoengineering. Also, a concern is that a rogue nation like India could decide to say, hundreds of millions of people, not that they are now, I'm just saying hypothetically, India could decide if in the future they say, look, so many people are dying every year because of climate change that we didn't do. We didn't emit this carbon dioxide. The West, America, emitted this carbon dioxide, but it's killing Indians. And so we are going to start putting aerosols into the atmosphere. We don't care about the effects of anybody else but Indians. We've looked at it. It's good for us. And so we're going to do it. But the effects could be really bad for other people elsewhere. So geoengineering, that's what they're talking about. Massive projects. Another one is carbon sequestration and storage, the CCS, where they try to pull CO2 out of the atmosphere and inject it into rocks and then hope that it doesn't melt or hope that it doesn't belch out. All of these projects are radically uneconomical. There is spending millions and millions and millions of dollars to create a test situation where they're absorbing the CO2 from the equivalent of a couple cars. None of them are tested at scale. David Wallace Wells talks about CCS in his video that you have to watch for the quiz. That's what he's talking about, is this carbon sequestration and storage that has never been done on a large scale, nor have they tried to do it for a long time period to make sure that the CO2 doesn't come burping out of the ground, making things doubly worse. What can you do? You can work to change capitalism. That's probably the most important thing. Other things you can do to make your life better that won't have a global impact. In fact, about your impact, don't feel bad about it. It's a systemic problem. Global climate change is a global problem caused by global actors. I used to have a CO2 quiz where you could find what your carbon footprint was. And I thought that was really interesting. And you could see the effects of like eating less meat or getting a car that gets better mileage and seeing how that would decrease your carbon footprint. But then I found out the carbon footprint was made up by British Petroleum to shift the blame from them to you so that they could say, well, it's not us. We're just supplying people what they want. It's you. You are the problem, but we're not the problem. The corporations are the problem. So things that you could do, you could drive an EV. EVs cost a third as much to operate as internal combustion engine cars. You could have a heat pump. You could electrify your house. We could pay for the electrification of everything in the United States off of cleaner air, causing fewer people to have lung problems. So the electrification of appliances is something that will continue to happen. But what can you do? Not a whole lot against global forces. And then just some things just to add in. One of the things that's going to be a really big deal is the shift in insurance markets. As wildfires become more common, as hurricanes become more powerful, insurance companies will not be profitable, and so they'll stop writing policies. They've stopped in California. Allstate, State Farm were not accepting new applications for home insurance. They're canceling policies. They're not writing new policies. So this is going to affect people all across the country who live in areas where they won't be able to get insurance. And if you can't get insurance, you won't be able to buy a house. You won't be able to sell a house because nobody will insure it. And if nobody's going to insure it, you won't be able to get a loan because nobody will give you a loan for a house in a fire-prone area without fire insurance. The same thing is happening across Florida. We can ignore that for now. The same thing is happening across Florida with companies not writing hurricane policies. And so the same thing is potentially going to happen across Florida. There will be a massive shift in economics as properties become worthless because you won't be able to get insurance. And if you can't get insurance, you won't be able to buy it. You won't be able to sell it. I included a bunch of articles. Hopefully they're good, about either carbon on Greenland or how sea level rise is going to affect people in Florida, how storms are changing their behavior, how flooding is changing its behavior. Another article on hydroclimatic whiplash going from drought to flood. Some more videos. This one on the effects on these different tipping points. Another video on Miami and real estate in Miami. What 3 degrees of global warming is going to look like. History of the Milankovitch cycles. This will give you some more better understanding of the Milankovitch cycles and how those work. More information on coastal cities and sea level rise in the future. And that's it for the chapter on climate change. I hope you enjoy the chapter. I hope you learn a lot. If you have any questions, please let me know.